Okay, so this is exercise 3, again from Ross. Yeah. And it's coming from page 407. Right? Now, in this case, we have two machines, okay, that are maintained by a single repairman. So there are two machines in a job floor. From time to time they fail, okay, or they break down. And then we have a single repairman who has to take care of both of these machines. Okay? Machine I functions for an exponential time with rate mu I before breaking down. So for each I 1 and 2, right, machine 1 and machine 2, okay, function for an exponential time with rates lambda, with rates mu1 and mu2 before they break down. Okay? And their repair times, on the other hand, right? Once they break down, of course, the repairman will come, right, and will take care of the broken machine. And the time it takes to repair either of these machines, so, okay, takes exponentially distributed random time with rate mu. So this is like the service time. So we have a one person who has just the same skill set when it comes to apply them to either of these machines. So therefore, it doesn't really make any difference how much time it takes to repair either of these machines. So it takes on average 1 over mu units of time to repair either of these machines. Okay. Now the question says, okay, construct a suitable continuous-time Markov chain and specify its transition rates and transition probabilities of the embedded discrete-time Markov chain, which he refers to the second part. What's the transition probabilities? Did we understand the question? Huh? Should we take notes, short notes? We have two machines, right? Machines 1 and 2. Okay? Right? May break down after an exponentially distributed or maybe I should say exponentially distributed random times, right? For each, they may be, of course, different. They are going to be different. Random times with means, or, okay, it means 1 over mu1 and 1 over mu2, respectively. Okay? All right. And we also have a repairman. We have a single repairman, right, who can fix a broken machine, whether it is machine 1 or machine 2, right, after an exponentially distributed random time as well. Okay, exponentially distributed random time, better actually, random time with some known mean 1 over lambda. Okay. All right. And we are asked to model this, right? The shop floor, perhaps, let's say, with a continuous time Markov chain. Meaning that we have to specify, well, define what the state is, what the states are in this case, and the transition rates and the probabilities. Okay. Now, what can we do in this case? Well, we perhaps use a pair to denote or to record the state of the workshop, shop floor, right? So ij, let's say, is the state or the status, okay, of, okay, machines 1 and 2, right? And each, okay, each of I and j, they stand for different machines, but they will take similar values. Okay. Each of I and j takes values u or r or w. U if the machine is up and running. R if machine is broken but is right now in repair. So our repairman is currently working on it. Right? And W is W if machine is broken but waiting for repair. Right? This can happen when? And since we have only one repairman, right? If both machines are down, if machine repairman is working on one machine, the other has to wait for the repair work on the other machine has been completed. Right? So we have to just either of these two machines can be in one of these three possible states. Okay? Then we can construct the state transition, okay, state transition rate diagram. Okay, how does that look? How does that look like? So we may have UU, right? Both of them are working. Both are up and are working. Right? If the first machine, as soon as the first machine breaks down, then this repairman will come and start taking care of that machine in no time. So it is going to be right away in status R. It is going to be in repair, while the other one is still working. Right? Both of these machines cannot break down at the same time. Right? Why is that? Because the time until machines, right, break down are exponentially distributed. Well, that's true only if exponentially distributed independent random variables. Right? So two independent continuously distributed random variables cannot take the same value, or, well, they can take the same value with probability 0. We don't know that? Huh? You have not heard something like that? Right? So x, y, continuously distributed. Meaning what? They have densities, namely, right? They have probability density functions. Let's say f and g, right? Even we should probably remind ourselves what this means. So these are non-negative functions that you need when you want to calculate, for example, the probability that x is near dx, which is, well, it is an integral, but now that integral is simply this, and right, y is in dy, y is near y, with probability given by gy dy. Right? And then you want to calculate the probability that x is going to take exactly the same value as y. How often or how frequently these two random variables can take the same value. Right? Okay, how do you solve this problem? Okay, this is like what? This is, we can condition on one of them, right? X equals y, given that y is near dy times the probability that y is in near dy. Like this, right? And when y equals y, so we can just replace this, right? Because now we know that y equals y, but then this is nothing but, well, since now these are independent, this is plain the probability that x equals little y. And how do we find this? We just take the integral of the density function of this guy, which is, maybe I should use x, right? The x over the set, right? From basically y to y, right? So this is nothing but the probability that x is in the interval from y to y, and then you remember how you calculate the probability that x is in the interval from, let's say, a to b. This is nothing but this probability summed from a to b for every x between a and b, right? For every x between a and b. And if you use the density function, so this is from a to b f of x dx. So we integrate that. But, okay, if, as in this case, a and b are the same, right? That's how you get x to be identically equal to y. So a and b are going to be the same. So you are basically integrating this density function f, not from a to b, but from y to y. Namely, it is just the area under the curve on the single point. Therefore, it is 0. Right? Well, this is 0, sorry. So in general, if you have an integral, well, if you are trying to find this probability, what you do is, this is nothing but just the area under the density function between these 2 points. If a and b happen to be the same, if they collapse, then of course the area is going to be 0 automatically. Right? You don't remember such things? Huh? The independence and the continuous, if two random variables are continuously distributed, so the probability of the event that x and y are going to be identically the same, therefore equals 0 all the time. Now I have the same story here as well. Right? So two machines, they break down after an exponentially distributed random time. We know that exponentially distributed random times are continuously distributed. We have the density function for them. Since they are independent, just the way x and y were independent over there, right? And then therefore, the probability that they may actually fail at the same time is going to be 0. So from you cannot move to any others. Well, I shouldn't say that. It is more complicated. They could have moved RW, I guess. I should first put them. Okay. What is more important here is that first one of them is going to fail and then the other, but not both at the same time. That is impossible. Right? So either the first one is going to fail, therefore it is going to go under repair immediately while the other is still working. Right? The second one is still working, or the first one is going to be working and the second one is going to fail and therefore is going to be taken to repair shop. Okay? So we will have one of these transitions. And from RU, where can you go? Either repair is going to, either repair is going to be completed or the other machine is going to fail. Right? Two events. If repair is being completed first, then you know that you are going back to this state. If the second machine fails before the repair of the first machine is completed, what happens? Well, the repair of the first machine has to go on, right? And the other one has to wait for the repair of the first machine to be completed. Here just the other way around, right? You may actually, okay, the second machine's repair may have been completed before the first working machine, the first machine fails, right? Or the first machine fails before the repair of the second machine is completed. So I must have forgotten this. So what is this? Okay, repair goes on the second, and the other one has to wait because there is no other repairman. And then from here, right, there is only one possibility. The other waiting machine cannot change its status. It is just standing there waiting for help, right? The repair, the state is going to change only if the repair on the first machine is completed, and in that case, the second machine is going to go immediately under repair. The other one is going to become up and running. That means we are going here, right? And similarly, this will just go to here. So these are the transitions. Now we have to figure out the transition probabilities. What are they? So if you are here, right, you can go to this state only after an exponentially distributed time, which corresponds to what? The failure time of the first machine. 1 over what? So that's the mean, but I need the rate, mu1. Okay, that's mu1, right? And if the repair is completed, right, on the first machine, is it lambda? It is lambda, right? Which doesn't depend on the machine, in fact. And we have the same argument, but in terms of the second machine. Right? The second machine fails at rate mu2, and it is being repaired at rate lambda. Okay, from here, RU repair, and the second machine is going to fail with rate mu2, right? And when we are here, only if the first machine's repair is completed, we will move out of this state, and that can happen at a rate lambda. Similarly, repair is going to be completed here, right, on the second machine this time at rate lambda, and you may move to this state if the first machine fails at rate mu1, right? Now we have the rates, right? Do we all agree with this picture? But we now actually want to know more, right? We would like to know the sojourn times, right? Or the rates of the sojourn times in all these states. So there is, okay, denoted by V, so it is going to be difficult to write all these pairs. Perhaps we should again enumerate all of them. Why don't we just do this now? Okay, we have a state space. We could have actually started with the original one, but let me just switch right away to this more compact representation. Now we can, with the sojourn time in state 0, no zeros, right? 1, 2, 3, 4, and 5. Okay. So the sojourn time in state 1, what does that mean? How much time the chain is going to spend there before it moves out to a different state? In this case, either to 2 or 3, right? What is that? Say it again. Mu1 plus mu2. Great. How did you find that? You sum the rates that are going out of this node, right? Why is that? That is the rate of an exponentially distributed random time, right? Their sum or what? When does the change happen? When does the change happen? Minimum of two things. Either the first machine or the second machine fails, right? The first time, whichever occurs first, the machine 1 or machine 2 fail, Now you will leave this state going to this one or that one, right? So if you just denote by T1, the lifetime of machine 2, and T2 by T2, the lifetime of machine 2. What did I say? Okay, lifetime of machine 1 and my lifetime of machine 2, right? Sojourn time in state, right? So these are, maybe I should write, lifetimes of machines 1 and 2, right? Then the sojourn time in state 1 equals the minimum of T1 and T2, right? And since T1 and T2 have exponential distribution, the minimum has to have also exponential distribution. That's a very important observation. And furthermore, its rate is going to be sum of the rates of these two guys, which are mu1 and mu2. So you know this result, right? So we don't have to go through the details. I mean, why this is true. Okay. And that's exactly what we need here, right? But mechanically, how do we get that? You look at the node and you sum basically the rates on the arcs going out of this node, right? Now we can just quickly do that for this one as well. 2 is this one, right? So you go out to this state 1 or state 4, rates were lambda and mu2. So this is lambda plus mu2 then, right? Because the sojourn time here is the minimum of two exponentially distributed random times. One is the repair time, the other is the failure time. Whichever occurs first, we will either go up or come down, right? Right, Alto? Okay. And the third one, state 3, so we go by this arc or the other arc, so the sum of the rates over these arcs is lambda plus, or let me write the mu1 plus lambda. For the fourth one, there is only one arc going out of this node, and it has lambda on it. And for the fifth, we have the same situation, right? So these are the rates. Now, by using this, we can always simulate, right, these exponential holding times. Sometimes we call also holding times this. You hold on the state for some time, right? The sojourn times, holding times, they are the same. Now, we also need to know these one-step transition probabilities, right? So we need to figure out what? Probability P01. Why do I like 0 so much? Okay, 1, from 1 to 2, from 1 to 3, one-step transition probability from 2 to 1, right? From 2 to 4. What else? From 3 to 1, and finally from 3 to 5. Right? We need to know these probabilities. Okay? Let's start with the first one. What is the one-step transition probability from state 1 to state 2? 1 over 2? Why? So is it equally likely to go like to the left than, right?
Not equal.
Perhaps not, because if this rate is 0, for example, that means you never go to here, or very small, let's say, if it is 0, it is unfair. If this is 100 times more than this one, right? Rate means it can open a lot faster. So it is not 1 over 2. What is it? Huh? Mu1? But mu1 can be bigger than 1. It is not a probability. It doesn't have to be a probability. It doesn't have to be between 0 and 1. Mu1 over this, right? Is mu1 plus mu2. Why is that? You remember something, right, from the past. But how did you find this one in the first place? This was what? It was related with the holding time, which you modeled or represented as the minimum of these two. Well, as soon as you leave, so we know that, what is this? This is the probability of moving to 2 as soon at the time when you decide to go outside 1, right? And at the time when you decide to leave state 1, you know that you will either go to 2 or 3. You know that. Actually, this is then the probability. Actually, this should be, before that, the probability that if I use the same T1 and T2, right? So the minimum, after the minimum of these two goes pass through, right? If the first machine fails before the second, then you know that you are actually following the left leg rather than the right leg, right? Only because the first machine fails before the second machine, U becomes R and U remains the same, right? If T1 is greater than T2, then you will move here. And in fact, this is the probability that T2 is the smaller of T1 and T2, right? Now, then that means that to find this probability, I have to calculate what? The probability that one exponential random variable is smaller than the other exponential random variable. And you know that they are independent. And there is the result, just this result which is famous, this result is at least as famous as this one, namely whenever you have two, so there are two important results. Whenever you have two independent exponential random variables, their minimum also has exponential distribution whose rate is the sum of the rates. And the other famous result says the probability that one exponential random variable is smaller than another independent exponentially distributed random variable equals the rate of the smaller random variable, in this case mu1, divided by the sum of these two. Therefore, you have that. That's what Ye remembers, right? And from here down, the smaller is this guy, right? T2. Therefore, its rate is going to sit in the numerator. But of course, you will divide by the same number, right? Do we have to prove this? Huh? You can prove that in the exam. Okay. 2, 1. What is 2, 1? So we are going from 2 to 1. Okay. From 2, where else can you go? 4, right? So there is a competition between 1 and 4, right? If you are going up, that means that the competition was won by whom? By the exponential random variable associated with this transition, which is repair. So repair, the probability of going from 2 to 1 is of course the same as the repair is completed before the failure of the other one. Right? Therefore, here in the numerator, you have the rate of the smaller of these two, in this case the repair time, which has rate lambda, right? You divide by the sum, or just this one, which is this. You get the same result, of course. Or in other words, if you want to calculate, let's do the same thing here. Probability of going from 2 to 4. 2 to 4, you look at the arc that goes from 2 to 4, you have mu2, so that should be in the numerator. You divide by what? You divide by the sum of the rates that are going out of 2, which are lambda and mu2. Right? And how about this? You tell me what this is. Probability of going from 3 to 1? Right. And finally, 3, 5, from here to there. Mu1 over mu1 plus lambda. Okay. All right? Right? Okay. So we will need all of these. Have I missed something? What happened to 4 and 5? 1 to what? From 4, you go to 3 with probability 1. From 5, you can go only to 2 with probability 1, right? Because you look at 4, there is only one arc going out of this node, right? You just divide the rate that you saw on this arc to the sum of the rates which are on the arcs going out of this node, but there is only one, and it is in fact itself, so this is lambda over lambda. Therefore you get 1. Right? So we are not really doing any exception if there is only one. Okay. Okay, great. So you understood this. But it is fun, right? So you have the big one paragraph, long paragraph of question, but it just boils down a pretty picture. Okay. And then we can also look at, well, there is this very famous subclass of continuous-time Markov chains known as birth and death processes. They are extensively used to model queuing systems, simple ones. All right. Let's look at them as well. Okay. They are also used, in fact, to model the population movements. That's from where the name comes from, in fact. Okay. Okay, suppose that a system, or the state of a system, is represented by the number of people inside it. Okay. So at time t, xt gives you the number of people in the system. Okay? For every t, non-negative. And whenever there are n persons in the system, then the time until the next arrival is exponentially distributed with some mean 1 over lambda 0. Okay? So whenever there are n people in the system, okay, an arrival will happen, right? Okay. An arrival will happen after an exponentially distributed random time with some mean which we will denote by 1 over lambda n. So we remember that there were n people just before this arrival. So lambda of lambda sub n. Okay? Okay? And we will assume that this random arrival time is independent of the so-called departure time. Departure, the time when a member of this population departs. Okay? That will happen after an exponential distributed random time with mean lambda n, which is independent of exponentially distributed departure time of one of its members, okay, which has mean, let's say, 1 over mu n. Okay? So, right? Either a departure or an arrival will take place first, right? If an arrival comes before a departure, then the population size is going to increase by 1. Right? If a departure happens before an arrival, then the population size is going to go down. Right? If an arrival happens first, then it is like a birth for us. Therefore, you have birth here. It's a birth happens, so population increases. Right? If a departure happens, that's like a death to us because this population size is going to decrease. Right? And these parameters, right, the rates. So these are the means, and lambda n mu n mu n are rates of respectively arrivals and departures, and the lambda n's. Okay, so we will have one for each from 0 to infinity, right? In principle, you may have arbitrarily large number of people in the system, according to this general description, right? These are known as birth rates, and mu n's are known. So when there are nobody in the population, right, birth rate is going to be 0. So we don't even have to worry about that. Death rate is going to be 0. Right? There can be no departures. So these are known as the death rates. Okay? And so this is, since all the changes happen only after exponentially distributed random times, independent of each other, this description immediately gives us a continuous-time Markov chain. In fact, X is a continuous-time Markov chain on state space consisting of non-negative integers, right? And then we can also specify or just draw its state, okay, transition rate diagram. What does it look like? We first put the states like this, right? It goes like this. So from state 0, you may move to state 1 if there is an arrival, right? Which will happen only after an exponentially distributed amount of time, and whatever the rate of that exponentially distributed arrival time, we will put it on this arc, right? That indicates at what rate you leave state 0 and you join state 1 through a arrival. So that's lambda 0, right? According to this description. From 1, the population can grow up to 2 at the rate lambda 1. So that's the rate of an arrival time when there is exactly one person in the system. When there are 2 persons, right, then rate becomes lambda 2. If it is 3, it is lambda 3. And if there is only 1 person, right, a departure can happen after an exponentially distributed random time with rate mu1, right? 1 indicating how many people there are in the system before the departure. And we made this population size can decrease from 2 to 1 at rate mu2, or from 3 to 2 at rate mu3, or mu4 from 4 to 3, and so on and so forth. It goes like this. So this is simple. And this is simpler than that machine stuff over there. What else do you need to know? But of course, again, so this is not enough, even though it contains all the information we need in order to simulate or understand the corresponding Markov chain. But anyway, while we are here, we can also write what? The rates of sojourn times in states 0, 1, 2, or in general n, if n is 1 or more, right? What are they? Mu0 is going to be what? Not mu0, it's v0. Okay. Say it again, lambda 0, because there is only one arc going out of 0. How about nu n? Lambda n? Is it enough? So this is supposed to be what? It is supposed to be the rate of sojourn time in state n. And this time is the same as the minimum of 2 things. Plus mu n plus 1. What? Just n, right? So when it is in 2, you have what? You will leave this state either by going to state 3 if there is an arrival, or by going to state 1 if there is a departure. The minimum of these 2 exponentially distributed random variables is going to give you the rate of the exponential sojourn time, right? Which is, in this case, the index is going to be the same, right? For 2, you have 2, 2, so you have the lambda 2 and mu2 summed together. So this is true in general. And then we will also need to know what? So they determine how much time the chain is going to spend before it moves out of any given state, 0 or n. But once the chain decides to move out, we also need to know where it goes, right? And from this picture, we know that it can go either a state less than itself or a state more than itself. Less than 1 or more than 1, right? So what is this probability? So this is the same as what? A departure happens before an arrival. And how do we find that? Huh? Mu n over. Good. And this? Right. Now here, an arrival comes first, therefore its rate goes above, and below you have, of course, the sum of all rates of all possible events, right? Associated with all possible events. Great. Okay. And this simple Poisson. Is Poisson also a continuous time Markov chain? Huh? Can we say that? You can. Suppose that mu n's are all 0, namely nobody is allowed to die. Nobody dies. Okay? And I am still talking about the same model, but now I am actually specializing to the values of lambda n and mu n, right? If lambda n equals lambda for every n, right? Then you have a picture, you can just copy them. 0, 1, 2, 3. And now there are no arcs going back, right? Because mu n's are all 0. You always go forward. You go with rate lambda from 0 to 1. You go with the same rate lambda from 1 to 2. And from 2 to 3, and so on and so forth. What kind of a process is this? What kind of a process is this? Now we are talking about a continuous time Markov chain where inter-arrival times, the process increases exactly by 1, right? You don't jump from 1 to 3. You always increase by 1, so it is counting something, right? It's counting how many people join to this system. And all the arrivals happen after an exponentially distributed random time with the same rate lambda. And they are independent of each other. And that was actually one property of which process? Poisson. We actually discussed in class, right? If you have a Poisson process, then the inter-arrival times, right? Inter-arrival times are exponentially distributed, independent exponentially distributed random variables with the rate the same as the rate of the Poisson process, right? So then actually the Poisson process is what? A birth process. But this is called a birth process. But in general, for a birth process, you have these death rates all equal to 0, but birth rates may differ from each other in general. If the birth rates are also the same, then that birth process is actually a Poisson process. Right? Okay. So this is a Poisson process, a homogeneous Poisson process with rate lambda, right? With rate lambda. Okay, it is a special case of a continuous time Markov chain then. Okay, we have that. What else do we have? Okay, how about this? Is it this or the other one? Okay, there is also this service systems, queuing systems, known as MM1, MMS, MMS and K, all kinds. They are actually all special cases of birth and death processes. So once we learn how to analyze, let's say, long run behavior of a bird and dead process, then you will have all the tools needed to analyze the simple single queue queuing systems. So this is another example. The MM1 queue. Okay, what is happening here? Now, suppose that customers arrive at a single server service station in accordance with a Poisson process having rate lambda. Okay, so this is like guarantee branch. There is only one person, I guess, standing over there, right? So you have to actually queue so that that single person can take care of each one of use business, right? If we assume that the number of customers, okay, arriving to the facility, okay, follows a Poisson process. What is this? Now a bird process, right? So there are arrivals after independent exponentially distributed random inter-arrival times. Poisson process with, let's say, rate lambda. Okay, and upon arrival, each customer goes directly into service. If, of course, the server is free, right? If not, then the customer joins the queue that is, okay. In that case, he or she is going to wait for the service, all right? And when the server finishes serving a customer, the customer leaves the system, and the next customer in line, if there is any, okay, will actually be served right after that, okay? And we also assume, right, the service times are also exponentially distributed independent random variables, okay? Service times are exponentially distributed independent random times with rate, I guess I use mu, alright, and there is single server, okay, and there is infinite length queue, right, or waiting line. Okay, so the facility is here, right? Facility is here. Then people come one by one, right, at different times. And when they come, they look at whether the server is free or not. If it is free, the person just joins this, will start receiving server. Otherwise, the person will actually wait in the line until his or her turn comes, and then he gets a service time exponentially distributed with rate mu independent of the service times of other customers as well as the other arrival times. Okay, so one stands here that there is single server. Okay, M here stands. Both M's are actually standing for Markov. The first one identifies the type of the arrival process. The second one identifies the type of the departure process, or the service process. Okay, M stands for the Markovian arrival process, which is equivalent to saying that it's a Poisson process. Okay, we saw that actually the only continuous time memoryless property, continuous time process with Markov property is what we define as the continuous time Markov chain, right? So now it discounts only the arrivals, so it's a Poisson. M identifies the distribution of the service times. Okay, it says Markov is equivalent with the memorylessness property. We already saw that if we are talking about memoryless processes, that's a Markov process. If it is a memoryless probability distribution, it's an exponential distribution. Okay? The first M4, the Markov arrival process, which indicates that arrivals are according to a Poisson process. That's hidden here, right? And the second one refers to memoryless service time, which says that the service times are exponentially distributed. Okay, and we have all this, and that you can just denote by xt the number of customers in the system, at time t. Right now, since all times before any state change are exponentially distributed, right? So this is also a continuous-time Markov chain. This process X is actually a continuous-time Markov chain on the state space consisting of what? There can be no customers exactly 1 or 2 or 3, while any arbitrarily large integer value, right? And okay, we have such a system. Now we can move quickly to state the transition rate diagram. Right, it is going to be like what? 0, 1, 2, and so on and so forth as before. And when there are no customers, right, nobody is going to leave this system, of course, right? It says the system state changes only when somebody arrives, and somebody arrives after an exponentially distributed random time with rate lambda. So we move from state 0 to 1 at rate lambda. When there is one customer in the system, it becomes 2 after an arrival, which is again exponentially distributed, again with rate lambda. So you see that the system grows, the number of people in the system grows with rate lambda. And if there is one customer, then that customer is the customer at the very beginning, or at the very beginning of the line is going to get served, and its service will end after an exponentially distributed random time with rate mu. So therefore, the chain moves from 1 to 0, state 0, with rate mu, right? If there are 2 customers, well, that means the server is still busy serving the customer at the very beginning of the line, and the service is going to be completed only after an exponentially distributed random time with now rate mu again, and therefore the chain may move from state 2 to 1 with rate mu. And that's, the story is the same, in fact, for others as well. So with rate mu, you can decrease, the population is going to decrease. With rate lambda, it may increase, right? So very little difference, right? And we can then identify rates of sojourn times, okay, maybe for 0, well, even they are all the same, perhaps, in this case, right? The time you spend in any one of these states has exponential distribution, which is the same as the distribution of the minimum of 2 exponential random variables. One, the arrival time of the next customer, and the other, the departure time. Departure is not possible here, so we have to take care of that separately. Now, it's clear for n 1 or bigger, then what I just said is true, and therefore you have lambda for the arrivals and mu for the departures. Here, as we said, just only an arrival is possible, you have lambda, right? And now you can write Pn, from 0, state 0, you can only go to state 1 with probability 1. Eventually somebody will arrive. But then probability of going from n to n plus 1, which is the same as 1 minus probability. I shouldn't do that. Okay. We can go to, well, to the right. If an arrival comes before a departure, which can happen with lambda rate, we divide it by lambda plus mu. And if you want to calculate the transition probability from n to n minus 1, right? This is going to be mu over lambda plus mu. In both cases, n has to be 1 or more. Right? Okay. That's it. Okay, let's give another 10-minute break and then come back and continue our discussion. Are there any questions? Probably not. Huh? Okay.